Hi, it's Dr. Khan with Chapter 17, which covers moisture, clouds, and precipitation. Here are the learning objectives for this lecture. 17.1 discusses the 6 processes which you'll need to know by which water changes from one state to another. You'll need to know the names of these transformations and whether or not the water is absorbing energy or if it's releasing energy. Heat energy is a form of energy that's measured in different ways, but one of them is calories. 1 calorie is the heat that it takes in order to take 1 gram of water and change it by 1 degree Celsius. So let's say we have water that's at 21 degrees Celsius and it's just a gram of water. The amount of energy needed to raise that to 22 degrees Celsius would be considered the heat energy of 1 calorie. Latent heat is what's called stored or hidden heat. This is heat that's added into a system, but it doesn't have the effect of changing the temperature of the system, which is kind of strange to think about, that we're adding in heat, let's say to water, and we're not changing the temperature. And this happens twice as we heat, let's say, ice all the way to water vapor. And it happens actually when we're changing the state of the water. So if it goes from a solid to a liquid, we need to invest extra energy just to do the state change. So instead of that energy being used to change temperature, that energy is being used to change the state. This is very important in atmospheric processes, as we have water vapor in the air that's condensing into cloud droplets or droplets of precipitation. So evaporation is liquid changing to the state of gas. We have to add energy in, and I think that should make sense to us. If we're trying to boil water, for example, we have to add in energy. As we add in that energy, let's say to a pot of boiling water, it gets to about 100 degrees Celsius. That's the boiling point of water. And we have to add in extra energy in order to get that water to actually change into water vapor. The amount in order to change 1 gram of water into gas is 600 calories, and that is called the latent heat of vaporization. Condensation is the opposite process, where water vapor changes into a liquid. And in order for that to happen, the water vapor, which has a lot of energy, has to give up some of that energy to the surrounding air. That is called the latent heat of condensation. In that same gram of water that we added 600 calories to get to change to a gas, that's the same amount that the gas would have to give up in order to change back into a liquid. Melting is when solid changes to a liquid, and notice it's less here. That latent heat is less for this process. For a solid to change to a liquid or to melt, we have to add energy, and again, that should make sense. If we're trying to melt an ice cube, we're going to have to add heat energy to it. But here, that same gram of ice, in this case, would only be an 80 calorie investment of energy in order to get it to change states. And then freezing is the opposite process, where liquid is changed to a solid. We need to release heat, so the liquid will release heat to the surroundings, and that heat of fusion is the same amount, that 80 calories for 1 gram. That's how much it would have to give up to the surroundings in order to become a solid. Sublimation is when solids change directly to a gas. Okay, this happens sometimes. You might notice especially if you haven't been in your freezer bin, your ice cube tray for a while, you might notice that over time they actually shrink in the freezer. Your ice cubes will shrink. In order for this to happen, notice that it's the 600 calories plus the 80 calories that we previously talked about of energy that had to be taken up by that solid in order to convert to a gas. And then the opposite process, I like to think of this kind of when we go out, let's say, to our car, in the morning and there's a bunch of ice crystals, those beautiful ice crystals on our window. That was our water vapor that was in the air that's changing directly to a solid without having gone through a liquid phase. And in order to get water vapor to go into a solid, you have to release all the heat, all the latent heat. And again, that would be the 600 calories to go from a water vapor to liquid, even though it skips that liquid phase, plus that 80 calories that it would have taken from a liquid to go to a solid. And that's what would have to be released into the environment. And your book has a good picture of that and a smart figure that's worth checking out. I feel like students are pretty good with evaporation and condensation, melting and freezing, and maybe the new terms here are sublimation and deposition. And those numbers you will need to know, so write those down, definitely. And we also have a really great molecular view of what's going on here. So this is water vapor, so H2O, 1 hydrogen and 2 oxygen bonded together. Gases have a lot of energy. They've absorbed that energy. Our water molecules tend to hang out closer together as they slip and slide past each other as a liquid. And solid ice, water ice, is a connected matrix or crystal pattern of H2Os. That are actually arranged in such a way that they're spaced out further than the liquid molecules are, which is why solid ice, I should say, specifically water ice, is less dense than liquid water, and that's why ice floats on the surface. That's why our ice cubes float on the surface, and that's why a layer of ice floats on a pond or a lake, for example, in winter. 17.2 talks about humidity. This can get a little confusing, I think, because there's several ways of measuring humidity, which just talks about how much water vapor is in the air. And there's a couple different ways to measure it that you would use in different situations or need to know in different situations. So what you've probably heard about is what's called relative humidity. It's a percentage base of what the air is holding compared to what it could hold. So if the weather report says it's like 90% humidity, you can feel that moisture in the air if it's a hot day. And then lower humidity, obviously a lower percentage. But that's not the only way that we measure humidity. It's just that that's probably the most useful way to measure it in terms of communicating to people about what it's going to feel like outside. So again, humidity is the amount of water vapor in the air. And we say that air is saturated when it's holding all of the water vapor that it possibly can. Now, how much water vapor can air hold? Well, this is kind of where it gets a little confusing sometimes too, because that number is not a fixed number. Let's say for a kilogram of air, the amount of water vapor that it can hold depends on things like temperature and pressure. So warm air can hold much more water vapor than colder air. And I think that's the key thing to note down here, that warmer air can hold a lot more water vapor than colder air. That's going to be kind of a consistent theme that we'll come back to. And then the concept of vapor pressure, that's total atmospheric pressure comes from all of the molecules that are sitting kind of above us and around us in this column of air. But vapor pressure talks specifically about how much of that pressure is due to water vapor molecules in the air. So how we measure humidity, one way is mixing ratio, and this talks about how many grams, it's the mass of water vapor. How many grams of water vapor are there in a unit of air, and let's say in a kilogram of air. So how many grams of water vapor are in 1 kilogram of air? So looking at that mass of that kilogram of dry air. So again, that unit becomes grams per kilogram. So maybe there's 7 grams of water vapor per kilogram of dry air. So that actually is telling us what the amount of water vapor is, like how many grams of water vapor are there in that unit of air. So you might think that that's very useful, and it is. That can tell us a lot of information. But again, since the temperature really dictates how much the air can hold, that ends up feeling different based on how hot or how cold it is. And that's why we have this relative humidity. It's a ratio of like how much water vapor is in the air And then compare that to how much water vapor would be required to saturate that air. So if it can hold 7 grams and it's holding 7 grams, that would give you 100%, 7 over 7, 100% humidity. So it's a comparison or a ratio that is expressed as a percentage. And again, that is going to change based on how much moisture there's in there. Maybe there's more moisture that comes off of Lake Michigan that's added into the mix, and so we have a higher relative humidity. Or maybe the temperature goes up. If the temperature goes up, humidity is going to go down because now it can hold more more water vapor, but it's not getting any more water vapor. So we have to think about that ratio in terms of its numerator and denominator. But here's the key thing, and I think that this is sometimes helpful for students to zero in on. This is an inverse relationship, meaning as the temperature rises, relative humidity decreases. Let's do that backwards then. As the temperature goes down, that same air parcel can't hold as much water vapor. So that the amount of water vapor that was in the air is constituting a larger percentage of what it can hold. So, said simply, as temperature goes down, relative humidity will go up. So, remembering that temperature and relative humidity are inversely related, as one goes up, the other one goes down, that'll be helpful to you. And here we have a scenario where we actually are changing different variables. I think this is a really helpful picture in the book, and it's worth some time examining exactly what's going on in this series of images. So the first thing I'm noticing here is that's at a constant temperature. So each of these 3 flasks here represent 25 degrees Celsius. So we're not changing the temperature in this case. We have a kilogram of dry air inside and 5 grams of water vapor. So our mixing ratio, our saturation mixing ratio, talks about how much, at that temperature, 25 degrees, how much water vapor in terms of grams can it hold? At 25 degrees, if you have a kilogram of dry air, how much can it hold until it reaches this point of saturation? And by the way, this information here is coming from a table in your book that gives you different temperatures and the corresponding number of grams of water vapor that air can hold at that temperature. So you're not expected to look at this image and know that that was supposed to be 20 grams of water. And you get that little indication here. See table 17.1 in your textbook, and that gives you what this amount should be. So in order to answer some of these questions, you will have to be given a table. You just have to understand what it means. And this table 17.1 is sometimes confused by students. I just want to make sure you understand that that table is giving you the maximum amount that can be held by that air. In other words, if there are 20 grams of water vapor in that air is saturated. All right, so now number 2 here is saying water vapor content is 5 grams. That's what we're given. So far this comes from the table. We're given this, and then we're asked to calculate relative humidity. Remember, relative humidity is a ratio that's expressed as a percent. So the numerator, or the top number, is how much is actually in this flask. So that's our 5 grams. So 5 out of how many? How many can it hold? That's our denominator. How much can it hold at that temperature? And that's from up here. So it's holding 5 grams out of the 20 grams that it can hold. So 5 over 20 gives you, if you do that in your calculator, actually 5, or just in your phone on your calculator, 5 divided by 20 will give you 0.25. But to make that a percentage, we multiply by 100, so we can use the percentage sign. So if you're following along with your calculator, that might be helpful. So 5 divided by 20, you'll get 0.25. But to change it to percent, we have to multiply by 100%. So we get 25%. Okay, in our second image here, more has evaporated. More of this water has evaporated into the flask. We're still at 25 degrees, but now this kilogram of dry air is holding 10 grams of water vapor. So in our first point here, nothing has changed in terms of our temperature. So the 20 grams that it can hold has stayed the same. But now our water vapor content has changed. We've added water vapor. such that we have 10 grams of water vapor. Now our part over whole, our 10 is our part, our whole is our 20. So part over whole gives us 0.5 in the calculator, and that times 100 would give us a percentage that's 50%. That makes sense, right? It can hold 20, but we're only holding 10. It's holding half of what it can hold. And in our third image here, more evaporation has taken place such that now there are 20 grams of water vapor in this flask. 20 of 20, so 20 of 20. The part that it is holding is 20, and it can hold 20. That's 100% saturation. Those are the kinds of math problems that you are going to be asked to complete. But again, you'd have to be given this saturation mixing ratio table so that you can look up for each corresponding temperature, what is the denominator? In other words, what can it hold? Now we're going to see a new set of flasks here. This is also in your textbook where the temperature is changing. We're going from 25 degrees Celsius to 15 to 5. But notice what is staying constant here. We have 10 grams of water vapor in the first and the second flask, but something different is happening in the third flask, where actually before we didn't have any water at the bottom, and now we do. So I want to first remind you that as the temperature decreases, the air's ability to hold water vapor will decrease. We cannot hold as much water vapor as it gets colder. So remember, the inverse relationship says as temperature goes down, relative humidity will go up. So let's take a look at that. Here it's the same information, saturation mixing ratio. The maximum amount that the air can hold at 25 degrees is 20 grams for every kilogram. And our water vapor content is 10 grams, meaning our relative humidity, it's holding 10 out of the 20 that it can, and times 100, that gives us 50% humidity. But now if we bring this down to 15 degrees Celsius, and if you take a look in your book, this is where that number comes from. This 10 grams is from table 17.1. When you look up how much can the air hold at 15 degrees Celsius, the answer is 10 grams. So now this flask is holding 10 grams out of the 10 grams that it can hold, 10 out of 10. That's 100%. And finally, in our third case here, we've reduced the temperature to 5 degrees. And looking at that table 17.1, it tells us that at 0 degrees Celsius, it can hold 5 grams of water. I'm not exactly sure what that says. 0 degrees Celsius instead of 5 degrees Celsius. Those two should match here. But in any case, I'll have to look into that. It's cooled to 5 degrees Celsius. And I think the idea here is that it's supposed to be able to hold 5 grams of water at that temperature. So it's holding 5. It can hold 5. So 5 out of 5 gives us a relative humidity of 100%. So what's happening here actually is that now this air can only hold 5 grams of water. If it can only hold 5 grams of water, it's not going to be able to support the 10 that was previously in this flask. In other words, condensation is going to happen. It's holding so much water for the temperature that it's like, I have to put some of this down. And that's what happens. We get water that starts to condense out and form at the bottom. How much water? However much water we need to get rid of in order to be back at 100%. So we cannot exceed 100% relative humidity. And that's one of the things that this graphic is trying to communicate with you. If you have a maximum of 5 grams of water, that's how much is going to end up as water vapor. And anything above and beyond that is going to have condensed to the bottom of the flask. Another way to think about this, if we had 15 grams of water vapor in here and cooled it all the way down so that the saturation mixing ratio was 5 grams, if we started with 15, we would have 10 grams of water at the bottom, because at the end of the day, we are only going to be able to hold 5 grams as part of this water vapor content. This image here gives us our idea of how temperature and relative humidity are related. So this says on a typical spring day in Washington, D.C., What you're seeing here is this inverse relationship that I was talking about before. What you have to think about, even though this is over the course of one day, think about the fact that the air, unless there's like a big storm coming in or something like that, doesn't really change very much over the course of the day. What I mean by that is that parcel of air that's sitting over the city of Washington, D.C. is pretty much going to stay the same. We're going to assume it's not picking up any more moisture, it's not raining. So just a typical day where it's pretty much the same air that's sticking around all day. What you're seeing here is that our lowest temperature that we hit throughout the night, at least on this day, and this is sort of typical, right? Like we haven't had the sun for all night and it keeps going down, the temperature goes down, and then the sun comes up and the temperature goes back up again. We reach our highest temperature on this day around, 5 p.m. or something like that, and then the temperature decreases again after the sun goes down. So what's happening with relative humidity? Again, we're assuming kind of like, here that our water vapor content isn't changing, right? It's just the temperature that's changing. So what we're seeing here is the temperature goes down in Washington, D.C. The air's ability to hold on to water vapor decreases. So it's the denominator here that's changing. Its ability to hold water as the temperature goes down. The denominator here decreases here from like 20 to 10, like it can't hold as much as it used to be able to. Therefore, the percent relative humidity is going to increase. So temperature decreases, humidity increases. But then the sun comes up, and as it warms the air, now the air can hold more than it could before. It's not going to. We're not taking up any extra moisture, so it's still the same amount of grams of water in the atmosphere. But the humidity is going to go down a lot because now the air can hold a lot more, but it isn't holding anymore. So our percentage goes down. And then again, the opposite happens after the sun goes down, starts cooling off, right? The temperature comes down. And therefore, that same amount of moisture that's in the air now constitutes a larger percentage of what can be held by that cooler air. So hopefully that makes sense to you, that inverse relationship between temperature and relative humidity. Dew point is a temperature. That's important to note. A dew point is a temperature. It's the temperature to which a parcel or unit of air would have to be cooled down to in order to reach that saturation point. So how cold do we have to make the air so that condensation starts happening? When we cool the air below the dew point, it causes condensation to happen. And we saw this back here with this flask over here. We cooled the water beyond its saturation point. And so condensation had to take place. We had to form this liquid at the bottom. So the dew point would be the temperature at which this happens, right? We cool it even a little more and it's going to form condensation. Now in the flask here, we formed liquid water, but other forms of condensation include dew, fog, and clouds. Dew, fog, and clouds are all water droplets. That's not vapor. Those are actually tiny little droplets of water. So water vapor, though, does require a surface on which it has to condense. So that's why often you go out to your car in the morning and there's dew, or the blades of grass have dew on them. Even cloud droplets have to form on particles like dust or smoke, pollution, things in the air, sea spray, things like that. So water vapor needs something to grab onto to turn from a vapor into a liquid. Our smart figure here shows dew point temperatures on a typical September day. What does this tell you? This tells you information here. How much would you have to, again, this is different temperature isobars here. How much would you have to cool the air to in order to maximize, or in order to get that maximum point where it's holding as much as it can and saturation has to happen? So what does it mean when you have a really high dew point temperature? If your dew point temperature is 70 degrees, that means you only have to cool the air to 70 degrees in order to get clouds to form, rain, precipitation. That feels muggy. 70-degree dew point, it feels gross, to be honest. It's kind of gross. What that means is the air is very, very wet and you're going to be able to feel that humidity. It wouldn't take much in order to wring some of that out. Dew points in the 50s are definitely more comfortable, right? So there's not as much water vapor in the air. We'd have to cool it all the way down to 50 in order to start feeling that moisture coming out of the air. And then take a look. This shouldn't be surprising either in areas that are desert-like and dry. There's so little water vapor in the air that you'd have to cool the air down to 20 degrees in order to get that water vapor to condense. So this is really very dry conditions here. Not a lot of water vapor in the air. A psychrometer is the tool that is used to measure humidity, and we do this by comparing two different thermometers that are sitting next to each other. One is called a wet bulb, so we literally wet a piece of cloth that's surrounding that bulb of the thermometer, and a dry bulb thermometer. So if the temperatures of both thermometers read the same number, let's say they both say 25 degrees Celsius at the same time, that means that we have 100% relative humidity. But if there's a difference between one thermometer and the other thermometer's reading, the greater the difference means the lower relative humidity. You guys have a sling psychrometer, I believe, in your lab kit. So that's something that you can actually experiment with by wetting the wet bulb and keeping the dry bulb dry. And you swing it around in the air and allow some of that water vapor, the water that's on the wet bulb to evaporate. If it can, the evaporation causes a cooling of the bulb, and therefore there'd be a difference in temperature. If a lot evaporated, you're going to get a much cooler bulb. So this brings us to why the temperature would be the same if the relative humidity were at 100%. If the air was already saturated, you're not evaporating water off of that wet bulb at all. So it's not going to cause cooling, and therefore the temperatures would be the same. So you can experiment with that, and I encourage you to do so over the course of several days where humidity is changing outside in order to see, do you get at the same reading? Do you get a different reading? Do it while it's raining, right? And see if you get numbers that are considerably closer to each other compared to a dry day. And that is how the sling psychrometer works. It gives you a little image in your book about dipping the wet bulb and then swinging around the thermometer. Just be careful of your surroundings. Make sure it's not near your desk or anything that's going to break the bulbs there. And that is it for 17.1 and 17.2.